At 06:17 a.m. local time, a Ukrainian Barracuda drone boat slipped into the Dnipro River outside Croissant, and the most immediate danger was not Russian fire. It was Ukrainian friendly fire. In modern warfare, the deadliest mistake often comes from your own side. The Barracuda crept low and quiet toward a Russian small boat forward operating base stacked with fuel drums, ammunition crates, and spare engines. The target was real valuable and exposed, but reaching it meant surviving a battlefield crowded with sensors and jumpy trigger fingers. As the drone cleared the last reeds and entered open water, a Ukrainian machine gun position roughly 500 ft upriver detected the heat signature and swung its barrel without hesitation. No warning, no questions, just instinct. 14 miles away, inside a hardened control bunker, the operator made the only move that mattered. He made none at all. He froze the controls and let the boat drift on momentum, knowing any correction could end the mission instantly. This is what modern war really looks like. Sensors over courage, discipline over firepower. And sometimes the greatest threat is standing on your own riverbank. For more sharp, no-nonsense naval warfare stories like this, hit like, subscribe, and follow Titan Navy. Above the river, a Ukrainian FPV quadcopter orbited at $1,000 FT, broadcasting a coded friendly signal, while the gunner below raised his night vision goggles and searched for the one detail that would stop him from pulling the trigger. Seconds stretched. 5, 7. Then he saw it. A pulsing infrared strobe mounted low on the Barracuda's hull, blinking in a pattern only Ukrainian forces were briefed to recognize. For a brief moment, everything froze. The gunner held his aim through the goggles, knowing that a single mistake would end the mission before it even began. He remembered his watch turnover briefing, lowered his weapon, and let the contact pass. The Barracuda had just survived its first and most statistically likely threat, and this problem is far more common than most people realize. One look at the Barracuda explains why. The hull is 18 ft of fiberglass composite light, enough to plane at speed, and tough enough to absorb small arms fire without catastrophic failure. It rides only 16 in above the waterline on a modified deep V hull that cuts through river chop while keeping radar cross-section low. In low light and thermal, it looks exactly like the enemy because it's designed to. Propulsion comes from a single 20 kW brushless electric motor, fed by lithium batteries, giving the craft roughly 4-hour endurance at patrol speed. At 8 knots, the motor is nearly silent, inaudible, until it's within 200 ft. At full sprint, that same system pushes the Barracuda to 38 knots, fast enough to outrun any manned Russian vessel currently operating on the Dnipro. In the bow sits a 35 kilon-shaped charge warhead, enough explosive force to gut a patrol boat, or today, detonate a fuel depot. And if the control link is lost entirely, the onboard GPS autopilot can execute a final waypoint attack autonomously. The Russians aren't just facing a remote-controlled boat. They're facing a system designed to complete the mission even when cut off. That reality is why thermal identification matters so much. A Ukrainian soldier scanning the river at night sees a bright streak moving fast and low and has maybe 3 seconds to decide if it's friendly before it passes. Guess wrong and hesitate, and a Russian boat slips through. Guess wrong and fire, and you destroy your own operation. There is no safe margin for error. To manage that risk, Ukrainian outposts receive precise corridor briefings at every watch change. Gunners are told exactly which lane a friendly drone will use, the time window it should appear, and the identification signal to confirm before firing. Mounted on the Barracuda's deck is a small device about the size of a hockey puck, an infrared beacon invisible to the naked eye, but unmistakable through night vision goggles. It pulses a pattern distinct from anything Russian forces use, silently telling Ukrainian gunners one simple thing: hold your fire. He checks his night vision goggles one more time, confirms the strobe code, and watches the boat pass without touching the trigger. But the infrared strobe alone is never enough. The Barracuda is deliberately moving at just 8 knots through the friendly zone, because behavior is the final layer of identification. At that speed, the wake stays flat, a thin, controlled ripple that looks intentional, not evasive, not panic. Russian sabotage boats sprint, weave, and zigzag because they are trying not to get shot. Ukrainian drone boats move slow and straight because predictability is part of the briefing. 3 conditions have to align every time: the correct corridor, the correct strobe code, and the correct behavior. Only when all 3 match does the gunner hold fire. The Barracuda clears the final checkpoint and slides into the transition channel, passing the last Ukrainian positions along the riverbank. At that point, friendly gunners can stand down, but another Ukrainian system cannot. As the drone boat enters the mid-river channel, it accelerates to 14 knots. Above it, the FPV drone climbs to roughly 1,300 ft to widen its field of view. Almost immediately, the video feed flickers. One frame freezes, stutters, then jumps forward. Something is interfering with the signal, and this time it is not coming from the Russian side. Every night, Ukrainian electronic warfare units blanket the river corridor with radio noise designed to disable Russian drones before they can reach friendly positions. That jamming does not discriminate. It does not know friend from foe. The front line is so saturated with drones that neither side risks leaving clean electromagnetic corridors. All it takes is one enemy drone stumbling into a quiet band, and suddenly you have hundreds more following it. So both sides flood the airwaves and let operators fight through the interference in real time. This creates a serious problem for the Barracuda, because the drone boat does not receive commands directly from the operator's bunker. The distance is too great, and the terrain is too cluttered. Radio signals travel in straight lines, but the Dnipro riverbanks are a maze of reeds, sandbars, and flooded forest that block, scatter, and absorb transmissions. A direct signal from the bunker would fade out within 3 puris amiti. To solve that, Ukraine uses a relay architecture. The operator's commands travel through a fiber optic line to a concealed transmitter site, roughly 8 mirrors behind the front line. From there, a tightly focused radio beam, only about 40 centimeters wide, is fired upward toward the FPV drone circling overhead. That drone is not a disposable scout. It is purpose-built for this exact role. The quadcopter escorting the Barracuda is a heavily modified DJI Matrix 300, a commercial platform originally designed for industrial inspection and mapping. In Ukrainian service, it carries a 15-watt signal repeater, a directional antenna array, and a thermal imager refreshing at 60 frames per second. The Matrix's original 55-minute flight endurance has been reduced to about 38 minutes due to the added payload, but that is still enough time to escort a Barracuda from launch point to target area. It typically operates between $1,000 FT and $2,000 FT high enough to maintain line of sight with both the ground transmitter and the boat, and low enough to remain beneath Russian long-range air defense radar coverage. The relay works by splitting the control path. Commands are received from the ground station on the 5.8 GHz band, then rebroadcast downward on 2.4 GHz to the Barracuda at close range. 2 frequencies, 2 transmission paths. Jamming one does not automatically kill the other. But the system is only as strong as its weakest link, and right now, that weakness is the drone boat itself. The Barracuda's antenna sits barely 10 in above the waterline. which is almost the worst possible place to try to receive a clean radio signal. Water reflects signals. Reeds absorb them. The river's surface fractures transmissions into overlapping echoes that overwhelm a receiver. Once Ukrainian jamming adds another layer of noise, the antenna can no longer separate real commands from pure garbage. The operator watched the live feed collapse into blocky pixels as control began to slip away. Latency spiked. The delay between joystick input and the boat's response jumped from 1/10 of a second to nearly half a second. At that point, no one is flying in real time anymore. You are guessing where the boat was and hoping your inputs arrive before it is too late. The Barracuda drifted 4 degrees off course, subtle but dangerous in water this confined. The FPV pilot reacted immediately. He climbed another 200 feet and shifted 200 feet east, lifting the relay path above the worst of the jamming and realigning it with the transmitter beam. The signal punched through. Latency dropped by another 1/10 of a second. The video feed snapped back into sharp focus. 2 quick rudder taps brought the Barracuda back on heading. Friendly jamming was now behind them. The relay chain had held. Ahead was something worse. A wetland labyrinth, flooded forests, submerged debris, unmarked sandbars, and somewhere in the darkness, Russian eyes already sweeping the water. As the Barracuda crossed into the flooded forest, the world went black. Reed walls rose 15 feet on both sides, killing ambient light and turning the nose camera into a useless screen. The operator abandoned the forward feed and locked onto the overhead view. The FPV's thermal camera looked straight down as the boat threaded through vegetation sandbars and half-submerged debris. This was where the Matrice's thermal imager justified its place in the mission. At 620 by 512 resolution, the sensor could tell a submerged log from a sandbar by temperature difference alone. Waterlogged wood holds heat longer than river silt. A 60 Hz refresh rate meant the FPV pilot saw obstacles in real time, not the half-second delayed slideshow cheaper sensors produce. In a passage, this tight half a second is the difference between sliding clean through a gap and burying the bow into debris. The Barracuda's electric motor pushed it forward at 6 knots. The hull slipped between reed clusters like a snake feeling its way through tall grass. Just fast enough to maintain control. Just slow enough to stop if the FPV spotted something at the last second. Speed is the enemy in a flooded forest. A submerged log at 20 knots flips a boat or snaps a propeller shaft. A sandbar at 20 knots buries the hull in mud and kills the mission on the spot. The operator eased the rudder. On the thermal feed, a faint white shape slid past the Barracuda's port side. A rusted barge hull half-sunk and completely invisible from water level. If the boat had held its original heading, it would have scraped the wreck and possibly torn open the fiberglass. The channel tightened again. Reeds pressed inward until the passage was barely 10 feet wide. The Barracuda's wake brushed vegetation on both sides. For the next 200 feet, the operator barely breathed, while the FPV pilot issued corrections in clipped single-word commands. Left, steady. Right, steady. When the reeds finally opened, the Barracuda slipped into a wider channel with real current, deeper water cleaner sight lines and room to maneuver. On paper, this looked like progress. In reality, the geometry had just shifted in the worst possible way. Inside the flooded forest, 15-foot reed walls had blocked line of sight from almost everything, including Russian observation drones. Out here, there was nowhere to hide. The channel stretched roughly 300 feet wide, with only low vegetation along both banks. The Barracuda's thermal signature was now exposed to anything that wasn't directly overhead. Its heat bloom could be seen from half a mile in every direction. On the thermal display, the FPV pilot first spotted a faint white speck moving laterally across the screen about 2,000 feet to the northeast. Then a second contact appeared, circling in a slow orbit above the Russian bank. They were no longer alone on this stretch of river, and the Russians were already hunting. The white speck stopped circling. It tipped over and dove. A Russian FPV attack drone dropping from 600 feet, accelerating straight toward the Barracuda's position. At typical FPV attack speeds of around 70 miles per hour, the operator had roughly 8 seconds before impact. Reduce throttle. Drift to the reeds. The order came instantly. Power was cut without hesitation. Momentum carried the Barracuda toward a dense reed cluster on the right bank. With the motor silent, its thermal signature began cooling almost immediately. The hull slid beneath overhanging stalks and disappeared into the vegetation. On thermal, the Barracuda became just another warm shape among dozens of debris piles and mudbanks. The Russian FPV screamed overhead, at about 50 feet, its camera hunting for a target that no longer stood out. It circled once, then twice, before climbing back toward patrol altitude. Without a clean lock, the Russian pilot wasn't about to waste his drone on a guess. But the second Russian FPV was already repositioning, and this one knew where to look. The operator keyed the radio. Relay to Boisville. Grid reference 47, Quebec Mike Delta, bearing 045. 2 hostile FPVs. Immediate suppression requested. 14 miles behind the front line, a Boisville Air Defense electronic warfare vehicle was already tracking the spike in Russian drone activity. Look closely at the vehicle, and you see a modified tactical truck with multiple antenna panels mounted on a rotating turret. Those panels are phased array emitters capable of focusing jamming energy into a 30-degree cone and directing it at specific threat sectors. Boisville operates across the 400 MHz to 6 GHz range, wide enough to cover every control link Russian FPV drones rely on, including the 900 MHz, 1.2 GHz, and 2.4 GHz bands common to commercial-based platforms. At full power, the system can sever a drone's control link from up to 10 kilometers away. But raw power isn't what makes Boisville dangerous. Precision is. Older jammers flood the entire spectrum with noise, blinding friendly drones just as effectively as enemy ones. Boisville doesn't work that way. It uses digital RF analysis to identify hostile signal characteristics, then generates targeted interference that attacks only those specific frequencies. Russian drones get suppressed. Ukrainian relay links stay clean as long as operators stay on separate bands. Tonight, they did. The Boisville turret rotated toward bearing 045. Antenna panels locked in. The system poured focused electromagnetic energy into the sector. On the FPV pilot's thermal display, the first Russian drone began to wobble its control inputs, turning sluggish as the jamming overwhelmed its receiver. 3 seconds later, it pitched forward and dropped straight into the river. The second drone fared no better. Its pilot tried to climb out of the jamming cone, but the Boisville operator tracked the movement and kept the beam fixed. The drone spiraled down and smashed into the reeds about 400 feet from the Barracuda's hiding position. The operator waited 10 seconds, eyes locked on the thermal feed, scanning for any new contacts. Nothing moved. The operator brought the throttle back up. The Barracuda slid out of the reeds and accelerated toward the final passage. Across several hundred feet of open water sat the target, a cluster of Russian outboard boats, fuel drums stacked on wooden pallets, and makeshift supply shelters glowing white-hot on thermal. The sprint was about to begin. But the moment the Barracuda entered open water, the Russians hit back with their own electronic warfare. And this time, They were aiming directly at the relay link. The video feed tore apart. One moment, the operator had a clean thermal picture of the target. The next, his screen dissolved into pixelated blocks and frozen frames. Latency spiked from 1/10 of a second to nearly half a second. Throttle commands stacked instead of executing. The Barracuda's heading drifted 5 degrees right toward a reed bank, and the operator couldn't correct fast enough to stop it. This was Russian jamming. A vehicle-mounted Sealock ZO-1 electronic warfare system on the left bank had come alive, flooding the river corridor with radio interference. The Sealock isn't designed specifically to stop drone boats. It's meant to disrupt Ukrainian FPV attack drones and blind artillery spotters. But at water level, the interference hits surface vessels even harder. The problem is geometry. The Barracuda's antenna sits just 10 inches above the waterline, the worst possible position to receive a signal during jamming. Radio waves from the FPV relay bounced off the water, scattered through the reeds, and were drowned out by Russian noise. The FPV drone overhead was still receiving the bunker uplink clearly, thanks to its altitude, but the connection from the FPV down to the Barracuda was collapsing. The operator understood exactly what was happening. The relay chain that kept the Barracuda a live bunker to transmitter to FPV to boat was being severed at its final link. The drone could still hear commands. The boat could not. The FPV pilot didn't wait for instructions. He climbed hard from 300 feet to 600 feet, then pushed 200 feet farther east. Russian jammers broadcast interference horizontally, focused on the altitudes where Ukrainian drones usually operate. But jamming has blind spots directly above the antenna and at steep angles away from the broadcast axis. Signal strength drops when geometry shifts. The FPV pilot was hunting for a gap in the jamming bubble, a clean angle where the relay could punch through. For 8 seconds, the Barracuda was steering blind. The operator had no nose camera, no reliable telemetry, and no certainty that his inputs were reaching the boat. He switched entirely to the FPV's overhead thermal view and steered by watching the Barracuda's white silhouette slide across the screen. Every rudder input was a guess. Every throttle adjustment was a prayer. Then the FPV found the clean lane. At 1,800 feet altitude and 250 feet east of its original position, the relay path cut through the jamming. Latency dropped back to 1/10 of a second. The video feed snapped crisp. The operator regained full control and corrected the Barracuda's heading with 3 quick rudder pulses. The jamming zone was behind them. The target was 700 feet ahead. Nothing stood between the Barracuda and the Russian logistics hub except open water. The sprint began. The throttle went to maximum. The electric motor surged, and the boat leapt forward at 38 knots faster than any Russian soldier could react. On the FPV's thermal feed, the Barracuda's wake flared white-hot as the hull planed up and the bow sliced toward the target. The Russians saw it coming. Figures scrambled along the riverbank, some running for cover, others reaching for rifles. None of it mattered. At 38 knots, the Barracuda covered 100 feet every 1.6 seconds. By the time the first soldier raised his weapon, the boat was already inside 400 feet. By the time anyone could aim, it was inside 200. The operator locked the rudder on the center of the boat cluster, while the FPV pilot called out the final distance. 300 feet, 200, 100. At 40 feet, the nose camera feed washed out completely in the glare of the approaching fuel drums. The operator released the controls. There was nothing left to do. The Barracuda's warhead was a shaped explosive charge designed to rupture thin-walled targets. Aluminum hulls, bolt holes, steel fuel drums, wooden supply crates. On impact, the charge detonated outward and downward, converting the drone boat into a pressure wave that struck everything within 50 feet at the same instant. The first Russian outboard boat flipped completely out of the water, its hull shattering before it slammed back down. A stack of fuel drums ruptured and ignited a tenth of a second later, sending a pillar of fire 60 feet into the air. The blast wave rolled outward across the bay, collapsing 2 supply shelters and scattering ammunition crates deep into the reeds. A second boat, still tied to the makeshift wooden dock, disintegrated into fiberglass splinters and spinning engine parts. The FPV drone jolted upward as the pressure wave hit at 1/800 feet, then stabilized and held position. Its camera never stopped recording. Secondary explosions rippled through the debris for another 15 seconds. Fuel puddles caught fire. Ammunition cooked off. Something heavy detonated inside one of the collapsed shelters. Burning wreckage spread across the shallow water, turning the bay into a floating inferno. Russian personnel fled inland, abandoning everything that wasn't already destroyed. When the smoke began to clear, the logistics hub was gone. The small boat staging area that had supported Russian raiding operations for months was now nothing but burning metal and shattered wood. Bye for now.